Everyone. Hope everyone is fine. Welcome to this fourth CCS monthly event, and today it's the May event, and this is a webinar. This is going to be exciting. Today's webinar is featuring Spotlight, and Elodie and Habib have nicely accepted to present this topic, which is quite overlooked generally about CCS projects, but key, which is monitoring and more globally MMV. Before I let Elodie and Habib present, I'd like to give you some information on the forthcoming events. As you know, we are trying at Force CCS to organize events every month. Unfortunately, it looks like June is a busy month, so there won't be any event as of now. And July is obviously holidays. But in August, we will have this on the 20th, we will have the annual network workshop at SODIR or NOD office in Stavanger, with centered around Paleocene plumbing systems. And with this, we will have the opportunity to look or to view and hear about core descriptions of Paleocene aquifers. Then we're trying to set up something for September. In October, there will be another workshop with modeling strategies for CO2 injection. And in November 19th and 20th, we will have a conference on the legacy wells, yet again at SODIR office in Stavanger. So then this event, for this event, there's a limited number of place. So of seats, so I think it's limited to 150. So I just encourage anyone who's interested in this conference to register now. This promises to be really exciting, with already a number of presentations and speakers touching various topics around legacy wells. We will have authorities. We will have organizations, we will have academia, of course, we will have even NGOs, at least Bellona. We will have, of course, companies. And with this, I think this is enough of me speaking. I will finish with saying that this webinar is recorded, so you will have the opportunity to watch it afterwards. And Elodie and Habib have been nice enough to accept that to tackle at least the easy questions in the course of the presentation. So please drop your questions in the chat, and those who will require a bit more elaboration will be addressed after the webinar. And with this, Elodie and Habib, the floor is yours.
Yeah, thank you. So I'm sharing my screen and the presentation. And I can see you on Habib's computer. So, okay. Okay, so hi everyone, I'm Elodie Morgan. I'm the co-founder of Spotlight. I'm a geophysicist, unfortunately. Maybe some of you are as well. So I've been working before in permanent reservoir monitoring and 4D seismic on Ecofisk mainly. And then it was 8 years ago, we founded Spotlight with Habib on the crazy idea of monitoring specific spots in the subsurface. At that time, we were still in the oil and gas industry. And 4 years ago, we decided to shift completely on CCS because the need was there. We need to make CCS at industrial scale a reality. And that's why an agile and a nimble technology can be useful to secure the CCS projects. And Habib, do you want to introduce yourself quickly?
Thank you, Elodie. I'm Habib Al-Khatib. I'm the other co-founder of Spotlight. She's the brain, and I'm doing the external stuff related to Spotlight. And I'm a geologist from educational background and a former CGG.
So let's tackle today's discussion. So the main discussion is about subsurface alarm. Do we need them for CO2 storage? So that's a huge question. Do we need an alarm, and which alarm can we use for CCS? So yes, if you have any question, drop it in the chat and Habib will see it right away. So talking about CO2 storage and monitoring, we need first to see what we have to do. And we have several regulation bodies that are telling us the main stuff that we need to monitor on a CO2 storage project. So we have international and the European CCS directive here. So I took this one because Norway is part of the international treaty and is concerned by the European directive as well on several projects. So here I will focus mainly on the subsurface monitoring, of course, and we mainly know that we need to be careful about the containment and the conformance of the CO2 storage in multiple ways. So that's where we will need a combination of several technologies, well, invasive technology, non-invasive, and we'll have several things to be careful about to have a monitoring strategy that can be viable for CO2 storage. So now let's see Norway. So Norway, you've mentioned it, Olivier, the Elodie is the main body that will tell what we need to monitor and why. So we've took some of the section about the monitoring here. You can see section 5.4 and the 5.5. So what we can see is that we have a lot about the model. We need to check the actual and the model behavior of the CO2 and the formation in the storage location. And this is something that we see as well in other regulation, like in Denmark, like in France as well. We see the same request of checking the mismatch between the CO2 in the formation and the model behavior. And I want really to emphasize that the model, is really at the center of many things. Well, it's not only for the regulation, but it's also to have a permit on the project. You will need to have a model, and we all need to have this model validated by many stakeholders. And it's the regulation, the European Commission, and it's also banks and insurance, and of course, the certification for ETS. So the model is central to all of the CCS project, and we want to show you a way to use it to trigger the right monitoring solution. So here, the main idea will be, of course, to check the deviation from the predicted model, and with the spot seismic, to have a frequent and focused monitoring to check the model. And thanks to that, we can have early detection of where the CO2 is and if we have a mismatch between the model and where the CO2 is. And we can do model calibration as soon as we can. And we can, thanks to that, secure, even more, the CO2 storage. And it's a way to do less, but still having the right information at the right time with an alarm system to secure the CO2 storage and to evidence that we understand what's going on and that we can model it and we can adapt the model accordingly. So that's what for the legislation part and how the model is critical in this legislation. So to recap, first, we need to check the model behavior versus prediction for the conformance and containment subject that we need to be careful about. We can use an alarm system to trigger the right intervention, and I will go back to that. When can we trigger something, and what can we trigger as well? And this way, we can have a frequent monitoring. Many regulations ask to have a monitoring solution at least once a year or to gather the data to evidence that we track what's going on in the CO2 storage. And finally, and that will be, also well, a red thread in this presentation, we need to be careful about the cost. We are talking about CO2 storage, we are talking about security, and not as much about optimization of a resource. So that's why if we want to build an MMV that is efficient, we have to keep that in mind. And how can we make the most of the security side while being cost effective? So now let's speak about the how. How can we monitor what's happening on the field? When can we monitor? When and why? So first, the most common monitoring tool that all CCS projects have is the in-well monitoring for pressure and temperature. So that's the basic technology, and this is a focus measurement, and I will show you some technologies that are focused and some that are, well, imaging technologies. So you have, of course, all of the seismic, the passive, the active seismic that we can use on the field. So the passive, the CSEM and the gravimetry, and of course, all of the active seismic technologies with 4D seismic, 2D lines and VSP. Well, in the active seismic section, we can find as well the spot seismic. We are still using one source, one receiver per spot location, but we are not providing an image. So that's why, well, it's in blue, and this is a focused measurement as well, just like you have an information with the in-well monitoring tools. Now, for all of these technologies, we have pros and cons. We have valuable information from all of these technologies to track the CO2 plumb, but you can see that in some cases, we still have this red thread, well, of cost. So for some of them, we don't have an image. For some, we have an image, but still we need to be mindful about the cost. So how can we use these monitoring technologies in a smart way? What can we do from the beginning, and what can we trigger, when and why? So to know that, we will go back to the regulation. So if first we have some cost-effective technologies, the in-well measurement, the spot seismic, passive seismic, and then we can discuss about CSEM and the seabed gravity as well. So if you have some cost-effective technology, we still need to be mindful about the regulation from the NOD, which is quoting the fact that we need to monitor at least once a year on the field. And to be able to build a monitoring plan that is cost-effective and to monitor frequently on the field, well, I will use what I was mentioning before, the mismatch with the model. Which technologies will give me an information about, well, a possible mismatch with the model, or just a match with the model, which in this case is a good information to know. So here, let's go simply. The most simple monitoring plan that I can think of, and we can discuss about that, is to have this in-well measurement, the spot seismic, and the passive seismic as well. This is the main thing that we can do at least once a year, and we can have data from these technologies, well, at least once a year, to show to the regulator that we are monitoring the CCS injection, the CO2 injection. So now, speaking about the mismatch with the model, when we have information with these technologies, we can see if we have a mismatch, and we can trigger the right technologies to mitigate and verify what's happening on the CO2 storage. That's where the more expensive technologies can be triggered, the VSP, the 2D line, or even the 4D seismic. So here, when in the case where we don't have a mismatch with the model, then we stay in the first level, and we can evidence that we understand what's going on. We can calibrate the model with the focus measurement, and we can have more predictivity with the model. And in the case where some measurements in some area show mismatch, we can trigger the right solution. We can be in a specific area first with VSP or 2D line to really highlight a critical area, or we can go full field if really something is going on the field that we can't explain. So that's for the technologies that we could trigger and why we could trigger them. Now, what I want to show you is that with a monitoring plan that looks like this, you have active seismic at every step of the way. You have active seismic from the beginning, and you can trigger more active seismic on the field if you need. And here, the way to have this active seismic solution anytime and anywhere on the field is to use synergies. We need for CCS to synergize, well, as most as we can, this acquisition effort that we have on the field. So that's what we've done. So I think this is the one that we've used in the UK. You can see this opportunity vessel that we've used. And because Spotlight is in less than a day of acquisition in some spot location, like 15, 20 spot location, then we can decrease the cost by 10 for the acquisition. And also, we have to consider, because of international regulation as well, we have to consider the ergon emission into the water, and this is even more critical in the North Sea. We know seismic acquisition is a huge subject, well, about the mammal environment and so on, so we need to be careful about the emissions that we make in the water. So for the spot seismic, we are using smaller ergon, like the VSP containerized kind of source that you can see in red in this slide. We use a small portion of the back deck of the vessel to place the source, and we can drop the nodes and operate the source in less than a day. The source is, on Greensand, it was a 600 cubic inch, and on Perenco, it was a 1,000 cubic inch kind of source. So that's something that will help optimize cost. The vessel can still do the maintenance on the area, and we just use it for less than a day to perform the spot seismic acquisition. So now, let's speak about a field that you might know quite well. This is Northern Lights. So this is the monitoring plan that was presented for the Northern Light field. And one thing we could ask ourselves is, how could we use the spot seismic on this field? They already are thinking about the in-well monitoring, the seismic monitoring for sure, well, in a passive way and an active way as well. With the spot seismic, you can have frequent information on how the CO2 plume is developing in the reservoir. So here we could have several spots at several steps in time and check if the model is validated or if we need to calibrate the model. And this way we can detect the variation, and we can have a spot monitoring every year on a field like Northern Lights. And you know which model is the right one as well. We know we have several models on the field, we never have only one, and we can check with some spot seismic, we can differentiate one model compared to another and make it more predictive. So that's how we can bring the active seismic right from the beginning and along the life of field of the CO2 storage field. So now that I've showed you how we could use active seismic on a monitoring strategy, let's see how the spot seismic is actually by what the spot seismic is driven, and we will talk about the predictive monitoring. The model will tell us everything we need to know and how we should monitor the field. So this is the quick sketch, and then in the next slide you will see this automated version of how we are using the flow model output. So here, just in a quick sketch, you have the detectable map of the CO2 in the reservoir at a certain moment in time. Then we have the detectable map of the CO2 the year after. Then you have several containment things on the field. You have an abandoned well, you have a fault, you have the license border. So these are things that comes from the risk assessment that was done on the field as well. So thanks to all of that, we can automatically know where to locate spots. And each one of these spots will tell us something valuable in the field while along the course of the CO2 injection. So the first one is a calibration spot. The calibration spot is made to monitor first the site of injection to calibrate also the petroelastic model and the modeling of the field. By monitoring the injection, we can see when we detected the CO2 from an active seismic point of view. Then you have the control spot in an area where we should not expect a CO2 change to have the sensitivity and the noise level of the spot seismic detection. So that's for the calibration spot. Then we have the conformance kind of spot. So here we use the flow model output. So at a certain moment in time and 1 month or 1 year after. And we can see that we will have spot location right where we expect to see an expansion of the CO2. And yes, the spot seismic will not see on the SAP side. That's right, because the main wheel of the spot seismic is to check for mismatch with the model. So if at some point in time, the CO2 is going south, in one of these spot locations, you won't detect the CO2. So you will know that something is going on and that the CO2 might be going elsewhere on the field. And that's when you can trigger more additional technologies to understand where the CO2 is going. So that's for the conformance kind of spot. Now, the last one, the containment spots. You have guardian spots that will monitor if the CO2 is going toward an abandoned well, and we can monitor several times to really check the velocity of the CO2 and going too close from this abandoned well, and so that you can decide if you need to make a recompletion on this well and when you need to do it. You have the fault, where you use guardian spot as well on each side of the fault to verify that your assumption on the permeability or not of the fault is true. And then light, the last one is a border license. You want to know how far the pressure or the saturation is going, so you can use a spot as well for you just to prove, well, if you need it at some point, that you did not go through the license border and in your neighbor's CO2 storage kind of field. So that's for the conformance and the containment spots. And thanks to that, you can have early detection on the field. And we know, thanks to the model and the risk assessment study, when and where we need to monitor. And that's important because the model is telling us when we need to monitor it. And thanks to that, for each kind of spot, we should have proactive decisions. The operator should know what to trigger if we see a mismatch with the model. And then can trigger the VSP, 2D, 3D acquisition if we need it. So that was the sketch view. Now let's see from an automated point of view how the conformance spots are located on the field. So what you can see here is the first version of the software that we are developing. So you can see we were talking about predictive monitoring and how we can use it, how we can use the detection result to calibrate and to check the dynamic model and the seismic response. So now on this image, you can see that we have several things. We have the saturation map, we have the horizon, and you can see it display on this image. So in purple, we have the saturation of CO2. So it should be the detectable CO2 saturation because still we are using seismic. So we know that we need a certain threshold of CO2 and we can study which level of CO2 we need to have a seismic detection. So here I will just play the movie so that you can see from the first year of injection, the CO2 plumb evolving, and you can see the spot, baseline and monitor, along the life of the CO2 storage field. So of course, each year we will adapt the plan, if we calibrate the model at that time, so that we can display the new spot location according to the latest calibration of the model. So that's how we can know, well, automatically, thanks to the flow model output, where the spot should be so that we can track the CO2 front in the reservoir. And for the containment, it's the risk assessment study. And for each of these this acquisition, we will monitor the containment spot as well. So that's for the spot location and how the predictive monitoring is working. So now let's see what we've done. So with Spotlight, we've been around for 8 years. What you can see here is the seismic data on the left side from the UK project. This is an acquisition that we've made in October. Well, it was a baseline from the Poseidon license with Perenco and Carbon Catalyst. You can see several seismic traces repeated over time. That's really important. Repeat the seismic shot, well, for 50, 100 shots. And that's what you can see here, as the blue points on this map, from this XY map, you can see the shot location. We know from a seismic point of view that the misrepeatability from source and receiver location is huge on the signal to noise ratio and on the repeatability of the seismic. So that's why we need to be careful about the shot location. And you can see here that all of these shot location were mostly around 1 meter in 1 meter in diameter. So that's much less than the conventional 4D seismic, where you have thousands of seismic shots to make, and you can't have repeatability really to the meter like this. But if we can, that's the best. So that's what we've done with Spotlight. We stay in a static way at each source location for each spot, and we shoot several times. This way, we can stack in time several traces to increase further the signal to noise ratio of the seismic dataset. And you can see in this graph in the middle, the impact on the normalized root mean square. So we begin at 40%, and then we can decrease the level of, we can increase the repeatability level, well, until less than 10%, in NRMS. So this is how, with the spot seismic, we can have the best signal possible. First, it's by design. We choose a source and a receiver location where we have the best signal to noise ratio based on the legacy seismic and the legacy shot gather. Then we choose the best weather condition, and we can do that in the North Sea. We've done it on Greensand and on Perenco. Between 2 storms, you always have, but at least 1 perfect day of weather. And the last one is a temporal stack. We can't use a spatial stack like 3D seismic and 4D seismic. This is something we will not do. So we need to use a stack in some way, because we know from a geophysical point of view, the main thing that will increase the signal to noise ratio is simply the stack. So we do it, but from a temporal point of view. So, yes, and the last one that you can see is that we have an optimal trace here, and we can match the legacy shot point and the latest acquired data, and we can still retrieve the reflection from the reservoir, from the underburden, and some reflection above, in this overburden, to still track how the CO2 is evolving in the reservoir. So that was for the data on the Perenco study. And I don't know, Habib, if you can do quickly Greensand, or do you want me to continue?
Continue. You're well launched.
Okay, so I just showed you the data from last year. And 2 years ago, we've done the Greensand pilot test monitoring as well. So it was the first spot seismic acquisition, and it was 2 years ago. And on Perenco, we've learned a lot from the Greensand one, so we were capable to increase the quality of the data on Perenco as well. So 2 years ago, Greensand, we had several spots that you can see in white. In yellow here, you can see the spot of injection. The blue triangle are the nodes that are dropped at the seafloor. And you can see in the red stars, all of the shot location we had on the field. We've used a 600 cubic inch seismic source, a small one, and yes, we had signal at the reservoir level. We've used an opportunity vessel, this was SVAC, and we use a node that you can see here. So at that time, the node stayed in place on the seafloor during 3 months, and we did 1 baseline, 2 monitors. Now what we will do is to retrieve the node, well, each time at each 30, so that we can drop it at the exact same location to avoid the node from moving well on the seafloor.
And allow the Danish fishermen to fish.
Yes, and allow the Danish fishermen to fish as well.
And that's in Denmark.
That's critical in Denmark. You don't want to mess up with the fishermen there. So here you can see the seismic results, and you can see baseline in the center, monitor 1, and on the right side, monitor 2. On each of this image, you have the seismic stack, and you have the migrated trace here in a little bit of shady white kind of color. And then you have the baseline trace, monitor 1 and monitor 2, post-processing. So this is after the temporal stack, this is after filter, well, and everything. And you can see that we reach a repeatability of 10 and 16% for monitor 1 compared to base and monitor 2 compared to base. We are a little bit higher for monitor...
For spot 2 and 27.
For spot 2 and 27, where we reach 23 and 36. So yes, I'm sorry, this was not base monitor 1, monitor 2, it's spot 7, 2, and 27. So yes, for spot 7 is really repeatable from 10 and 16%. Spot 2 is a little bit less repeatable with 23 and 36. And spot 27, we are a little bit higher, but still we can have a detection with that. We have 36% NRMS. So here you can see on spot 7, the spot section, the migrated trace, base monitor 1 and 2, and you can see that we don't have any amplitude effect at the top reservoir. From a modeling point of view, we were expecting to see an amplitude effect because it was the saline aquifer part that they were injected the CO2 into for the pilot test, and that's why we were expecting to see this amplitude shift. So you can see on spot 2 that we don't have an effect, and spot 27 here, you can see that as the top reservoir that is in blue, we have a quite noticeable CO2 effect because we can see an amplitude change really at the location of the top reservoir. One thing I want to add here is that it was only 4,000 tons of CO2 that was injected into the reservoir, far less than what they were expecting, but it's still 4,000 tons of CO2. It's not much, and it's, yes, we were able to see a CO2 effect on this spot 27. So we had many spots, and that's how we were able to monitor all of the green sand field from the pilot test point of view and to manage to have a successful detection. We have many technical papers on that, so if you want to know more, we can also, you can find all of the paper on the website as well, the Spotlight website.
For Q&A.
And we can discuss about it in the Q&A, yes, as well. So this is my last slide. So we saw how we could have a monitoring strategy that is agile and nimble using the spot seismic, the in-well measurement, the passive seismic, and triggering the right technology when and where you need it, and if you need it. So here on Greensand and Perenco, we've used the opportunity of this injectivity test to do the spot seismic at this specific moment in time, because this will help the operator to calibrate the petroelastic model. And then, well, of course, we can monitor for the full injection phase to check for model deviation, to have also, from an MMV point of view, an increased social acceptability for the fishermen, for the maritime traffic, and so on. We can take all of that into account to have a spot seismic acquisition that will respect all of the stakeholders that will be on the field at some point. And by showing that you can have a detection of model mismatch on the field at least once a year, that's something as well that you could use to convince banks and insurance to invest in your CCS project and to secure your CCS investment. So yes, that is all I wanted to show you for today. And if you have any question, it might be technical from a strategical point of view, we can discuss about it. And I would like to thank you all for being here tonight or this afternoon for you.
Thanks, many thanks, Elodie. Very interesting. I think this methodology ticks a lot of boxes, not the least the costs. I see there was a hand that was raised. I think it was Louis. Was it?
I was just sending applause, not.
Thank you.
Excellent. Are there any questions? There was no question in the chat. Don't hesitate. This is, FORCE is a place to share and learn and exchange. So this is the place and the moment. If not, just a few. Well, and waiting for questions. I have a few things. The former webinar we had with FORCE CCS, it was use of tracers. I don't see this named in your presentation. I think all or some of the methods are definitely complementary, and you showed that to some extent. But the use of tracers seem to be very interesting.
Tracers.
And we had the former webinar was on that, and they will be presenting like you during the conference on the legacy wells. So it might be interesting to exchange on that. Yes. I see Selina had a question. Selina, do you want to read it yourself or to ask your question yourself? Or
yeah, hi Selina.
Yeah,
yes, if you want to. Yeah, hi.
Hi, how are you?
I'm fine, and you?
Fine. Thank you.
Thank you for being here.
Yeah,
and if you want to tell me,
I have a question for the spot seismic.
Yes.
Can the signal amplitude or frequency recorded at seismic spot be used as a triggering threshold in an automated alarm system?
Okay, yes, I see what you mean. So if I understand well, is the amplitude level of the frequency recorded can be used as a threshold. So what can be used today as a threshold from a spot seismic point of view is the fact to detect or not. We are still not quantitative because we are using one antenna to monitor what's happening on the spot. But what we want to check if we have a mismatch with the model. So two cases, we don't have a mismatch and we are good to go when the alarm will not go on, or we have a mismatch with the model. And depending on the criticality of the spot, then you have an alarm and you can decide what to do, a model update, VSP, or more than that.
There is also another aspect I can complement on that, Selina. It's the fact of having a static repeated shot allow you to do also some statistics, and using this statistic you can define if the measurements can be trusted or not. So that's also another aspect. And the last aspect is also about what Elodie mentioned as a petroelastic calibration model calibrations. which was the black spot in your drawing, where in fact, if you monitor a spot exactly co-located to the injection wells, at this injection well, you know precisely how much you inject, what is the saturation, and what is the pressure. So by monitoring frequently, and in the case of Perenco, we monitored, a full day of injection just to check the pressure effect. Then you can answer the question, is the pressure increase, at least at the well, at the injection point, high enough to be detected with active seismic? And to be honest with you, Selina, if the answer is no, because active seismic in this specific geology can't detect pressure, it could be even a good news, because at least that means you don't need to waste your money in a full 4D for conformance, because it will not be useful. So that's a kind of quick complementary actions from spot seismic as a threshold, just like you said. So it's your question is very wide and can be answered several ways. Thank you for asking.
Thank you, Selina.
Thank you. It's clear now.
Yep. Sorry. Somebody else? I have a question, a quick one. It's awesome that you can show practical examples and real examples. It's amazing, by the way, that you got permission from Greensand, Ineos, and partners on one hand, and Perenco and partner on the other hand, to be able to show these examples. This is really key to understand the practical use of it. Can you, while you are speaking about Northern Lights, if you can, and only if you can, are you working with Northern Lights, or do you have contact with Northern Lights? What is their reaction? And do you work with other licenses on the NCS, if you can tell?
So we are discussing with several people from Northern Lights. From where we are right now, is that the spot seismic is not integrated into the Northern Light monitoring plan, because from the latest data that I had, it was mainly 4D seismic that will be used on Northern Lights, and that will give the full information on the full field. So of course, if you can perform a 4D seismic, that's the best thing to do. You have the full information. On some of the cases, you can't do 4D seismic as much as you want, and sometimes you really can't do it. It's the case for the Poseidon license with Perenco. Well, it was the case from Greensand as well. It's the area and the kind of operators that can't afford to do a 4D seismic at some point. So that's why we need to be, to think differently, to have a monitoring plan that will be cost effective and still giving the right level of information of the CO2 storage, plumb, and so on. So yes, on some cases like Poseidon, we are working on that. We are working as well. We were working with the Danish, and we are working in many projects in North America as well, where they need to evidence to the regulation that they understand what's going on and that they have tools to monitor the CO2 plumb.
It's onshore, US?
Onshore, yes.
Yes, it's onshore.
So
yes.
that's even more critical. Mm-hmm.
Yes, we have many technical publications as well. Onshore in Canada, we've been monitoring for quite a while the Weyburn field for CO2 as well. So yes,
we should present. We validated spot seismic against full 4D on the Whitecap Weyburn area, and that should be published. I hope in Ottawa, Toronto, not Toronto conference, EAG conference in Toronto, not Ottawa. We should receive the agreement from the client in some days to come now. What is also very interesting is, as Elodie is saying, there is two kinds of clients. The one that have a lot of money, and also it's a pioneer project where safety is paramount, and full 4D, at least at the start of the project, is key. But even in this case, and that's the example we hope to show you in Toronto, even in this case where you have frequent 4D seismic like every 2 years or every year, even in this case, having spot seismic in between the 4D without triggering the 4D will give you, and that's what we prove on this Canadian example, will give you calibration point to understand the dynamic behind the image, because the image is just a time lapse between a year and 2 years after or 4 years after. This dynamic calibration point every year, you can connect the dots and say, hey, actually in 2023, there was no CO2 here, while in 2024, with the full 4D image, I see CO2 here. So that means the CO2 is recent in this area.
And
so
that's,
that
and
is
that's
for
why,
me a very important point.
And that's why I'm before we tackle or address Selina's other question, I just want to follow up on the initial question about Northern Lights. You know, even though they have the luxury of having a 4D seismic and shooting 4D seismic, they may be interested in lowering their costs by maybe postponing the 4D, because that's the aim, right? So I was interested in knowing how they responded to this technology with regards to potentially optimizing costs.
Yes. So I think the best is to ask them directly on that.
Okay, I think
Olivier, but
okay, that's fine.
But yeah, because they answer us this, but I don't want to say
No.
I don't want to disclose what they answered.
No.
You might be surprised.
Okay. Okay. In any case, Selina had another question. Sorry, Selina. So your turn.
No problem. I have a question for seismic spot. Are seismic spots more suited to capturing sudden events like microseismicity, or can they also detect slow CO2 migration over time?
So for the spot seismic, it's still active seismic, so we are sensitive to the same kind of event as VSP, 2D line, and 4D seismic. So it's mainly saturation, pressure, and for the microseismicity, you might have other technologies that will be sensitive to that. And still, if you have a microseismic event somewhere, that could trigger a spot seismic acquisition there to verify if we have CO2 in this area from a saturation point of view, if we can detect it, if the level is enough. So yes, microseismicity, it will not be detectable with the active seismic technologies, but you have other tools to detect that. And that's why I was mentioning passive seismic and so on, because you have a good combination of technologies together to really detect several kind of events.
Okay, thank you.
Yeah, thank you.
Good. So now we have a question from NOD. And I suggest Christopher, I'm happy to see you here. Christopher, do you want to ask your question yourself?
Hi, Christopher.
Yeah, hi. Thanks for presentation. Very interesting indeed. I'm just curious to ask if you have made any sensitivity analysis on the cost side, like what would the business case look like for a full field and full cycle economic study on the monitoring if you can skip certain other monitoring procedures, like if you can skip one 4D survey, how would the total cost picture look like?
Mm-hmm.
So that was in the backup slide.
Yeah.
Okay.
So thank you for asking.
Yeah.
Thank you for bringing in the backup slide.
Hey, you guys got an agreement before?
Yeah,
absolutely.
Absolutely. So I send the bill now.
Very.
Yeah. Yeah, so this was on the backup slide. So we did a study actually to compare 30 years of monitoring using spot seismic and 4D. First, you have the 4D only. So of course it will depend on the field and so on. And I don't know if you have more info.
It is exactly mimicking the Northern Light acquisition layout. I mean plan with the full 4D, and it's also taking into account the fact that they said that at the beginning of Northern Light they will only shot a small portion around, not the full 4D. So that's why the cost of the last 4D is huge, because the area after 25 years of injection will be massive. So yeah, this one is indeed, it's based on public info, but that's the kind of cost you can anticipate from a full 4D. And then we are developing, and by the EAG, we will launch a platform where everyone can do this kind of value of information. So Chris, your feedback will be highly appreciated. We'll send you the link. But this is an example where you save a single 4D, which is the last one, because we say that in Norway, especially on Northern Light, they don't want to save cost. They want to first to get in between 4D, more frequent data, more warnings, but their model is right, and they demonstrate to the NODs that everything is fine, and they just keep the last monitor. In this case, indeed, the value of information is still here, but we are talking about, I will say, only 5 million at the end on 30 years. If you do that and you only skip 240, but unfortunately for you, you didn't skip the last 40, then the value of information is slightly less or similar.
So each bump here is a 4D seismic.
But the cost of Spotlight of Spot Seismic is integrated into it, not Spotlight. Yeah. Everything, acquisition, processing. And that is if you manage to only save the last full 4D, now the costs start to be very sensitive. You are talking about something like nearly 20 millions. And indeed, if you are very good in your forecast and you're able to show to the world and to the NOD that every time you detect there is a match, then maybe you can skip the full 4D to finish with and do some 2D lines around where you expect the CO2 plume to be. And in this case, yes, obviously the savings are massive. So indeed, it's case by case dependent. It depends on which full 4D you saved, when you saved it. But I think this is answering your question, right?
Yeah, thank you. It's just to have a view on the business case, what you potentially propose to replace with your technology. That's what I was after.
Yes, of course.
Yeah, we don't say replace because it's really postponing, phasing.
Yeah, so we don't use a replace because we know that we don't provide the same value as the 4D seismic. So it's not a proper replacement as per se, but it's really, yes, a different way to monitor and to verify if we need to trigger more expensive technology. So we are not a replacement of 4D seismic, really. We are not providing the same information as 4D seismic. And if one field really needs 4D seismic, then they should have 4D seismic, but they should know why they need 4D seismic.
Which means also that you as a regulator will impose to this operator to do the 4D seismic because they need it. And you can explain the environmental disturbance to the mammals and so on based on that. And I'm also curious to know, because I don't see that many often in the CCS surveillance topics discussions, but what if Norway ban air guns? Does that mean that every full 4D baseline that has been acquired with air guns had to be reshoot with marine vibes? Because if that is to happen, then it's a kind of a hell of a cost for the industry as such, where with spot seismic, it's easy to understand that with a single shot, with a single spot, you come for one extra day, so 2 days instead of one, and you redo your spot baseline with the air guns and with the marine vibes to the same locations, and then you roll after with the marine vibes. So do you think that this is a topic, Chris, that we should address more in the CCS market, the possibly ban over 30 years of air guns, or this is something you can't comment, or you don't think it's a topic?
No, today this is no, it's today this is not, well, it's a topic in the sense that environmental restrictions are already there in place. So there are times in the year when you cannot kind of go out. So obviously there are some limitations, but so explicit as you describe now, that's not a topic as such today.
Okay, great.
I have a follow-up question on that graph, Elodie and Habib. Did you account in the cost for precisely the emissions or not? In the cost.
Yes, yes. The emission you see here is accounting for the emission. Yes.
Assuming an ETS price.
No. It's sorry. It is about the acquisition emissions
No,
due to the
yeah.
seismic.
And you don't offset because you, if I understand well, if you skip one 4D seismic, you spare 26,000 tons of CO2 equivalent emission.
Correct.
So
Yeah,
that
correct.
means you will not be we will not pay a tax on these emissions. Did you
Correct.
integrate that?
No,
That's
No.
a good point.
that's not taking into account. in
But
the
let's
graph.
work together.
Yeah. Yeah, you're right. No, but that's a very good, a very
Yeah.
fair point. No, the cost is purely on acquisition and
fine.
processing cost.
I understand.
Typically, to give you a range, a spot seismic yearly is all rounded in the range of 200K, where a full 4D will depend about the size.
Yep. Okay, I see that people are bailing out now. I mean, we all have busy days. I would like, on behalf of Force, to thank you very much for this very interesting presentation and for the effort for presenting from Melbourne. I hope the weather is as fine as here in Norway. I would like to thank everyone for attending, and again, I don't think there will be any event in June, neither in July, but please register yourself for the forthcoming events in August, September, November, and December. And with this, I wish everyone a very good day and hope to talk to you soon, anyone.
Thank you. Thank you very much for having us. Bye. Have a
Bye-bye.
nice day.
At
Bye-bye.
Bye.